We live in a macro world where everything has a definite shape, occupies space and behaves predictably. We're used to the idea that thin materials tear, fragile things break, ice chills, flames burn and water flows downwards. Yet when the opposite occurs, we're left speechless. For centuries, magicians built their careers on these unexpected phenomena. In 1983, the most famous illusionist of our time, David Copperfield, stunned the audience by making the Statue of Liberty disappear. The effect was mind-blowing, and to this day it's hard to tell exactly how he did it. Through his act, Copperfield managed to shock the audience by challenging our understanding of reality, making it look as though the statue really disappeared. However, intuitively we know that the Statue of Liberty didn't actually vanish. The audience just couldn't see it for a moment. But do you think there can be something both outstanding and genuine in our world, something that doesn't involve magic tricks? The answer is a resounding yes. And today you'll witness real wonders firsthand without any tricks. Get ready to see a liquid flowing upwards, a boat floating in an aquarium without a drop of water, dry water, hot ice, and many more unusual and astonishing things. Substances that defy the laws of physics. Likes support videos and help the YouTube algorithm promote high-quality content. Please leave a thumbs up to support this video. What we are about to show you is not an illusion, and that's the most important part. There are real materials and structures that genuinely exist, and even David Copperfield wouldn't envy their astonishing properties. Some might seem impossible to you, but rest assured everything is real and strictly follows the laws of physics. Clearly there's more to this world than meets the eye. With that in mind, let's move on to the first item in our collection. At some point, nanotechnology experts came to wonder what would happen if you vertically aligned many carbon nanotubes and pressed them close together. How would such a material behave? The developers of Surrey Nanosystems were the first to come up with a practical answer. They created Vantablack, the darkest substance in the world. Vantablack is a honeycomb comprising of millions of carbon nanotubes. However, unlike in bee honeycombs, its carbon cells are empty. Although this structure is quite unique, its most important property is that it almost completely absorbs electromagnetic radiation. What does this mean? It means that it's possible to make an aircraft that doesn't reflect radar signals, optics without glare from scattered light, some new designs and much more. Don't you see the implications? To fully understand Vantablack's effect, imagine being in an empty room with the ceiling, walls and floors covered in Vantablack. There's absolute darkness and void all around. You turn on a flashlight, but it doesn't make any difference. As long as the flashlight is pointing sideways, it doesn't light up anything, and you can't even see its beam. You might see a hand and legs when pointing it directly at yourself, but other than that, there's nothing around but a pitch black void. If you pointed the flashlight ahead and took a step, you'd bump into an invisible wall. That's what 99.965% absorption means. Due to this property, we see any object with such a coating as shadowy anomalies against other objects. Its unmatched absorption makes it impossible to distinguish detail, see relief and shape. Any sculpture coated in Vantablack would be perceived as a two-dimensional silhouette made of black paper. Thanks to the ultimate black body effect, Vantablack has already found applications in aviation, car manufacturing and, of course, in space. What you've just witnessed was the uncanny ability of Vantablack to hide an object's texture, blurring the lines between reality and fiction. As impressive as this might be, you might want to hold on to your socks right now, cause we're about to knock them off. This stuff sounds totally like something ripped straight from a sci-fi epic. One of the most reoccurring motifs in movies involving time travel and alien visitors is rapid wound healing and body regeneration. For now, these remain science fiction. However, the real evidence suggests that we might be seeing the dawn of such technology. You're about to see polymers capable of rebonding after being severed. Moreover, this reintegration neither involves loss of original properties nor any external intervention. Meet the PDMS Ssip BNB, an absolutely unique polymer with an innate flair for self-repair. Similar to futuristic robots, this material can seamlessly mend itself post-breakage without the need for adhesive, welding or any other tricks. Developed by scientists from Tianjin University, this elastomeric polymer has quite impressive resilience. It can regenerate even under low temperatures in fresh or seawater, and even in an aggressive chemical environment. While it's too soon to talk today about instantly regenerating human muscles and skin, this new polymer is sure to find applications in robotics, aviation, and automotive production. Imagine a car that can self-repair interior linings or a leather sofa fixing its upholstery all by itself. What's even more impressive is this polymer's ability to be transformed into a conductor by adding iridium and gallium. Just think about self-reparation electronics. What if you broke a smartphone in half only to see the two halves join together and merge within minutes all by themselves, turning into a fully functioning smartphone? The extraordinary properties of PDMS Ssip BNB push scientific achievements into the realm of sci-fi. While many modern materials astound us with their capabilities, we know that their production often involves complicated processes and sophisticated equipment. Fortunately, there are some exceptions where even the simplest processes can yield a super material. The discovery of graphene is one of these rare, almost magical moments in science. You might find it hard to believe that two young Moscow State University graduates, equipped with cheap adhesive tape, were the first to obtain graphene and subsequently even a Nobel Prize. Yet this is exactly what happened. In 2004, Andrei Geim and Konstantin Novoselov attempted to separate graphite into individual layers using adhesive tape. Multiple tape exfoliations later, they obtained a layer only 1 atom thick that one could see with the naked eye. This was the first piece of graphene. Further research revealed a plethora of graphene's unique properties. As it turns out, it's an excellent conductor of electricity and heat. And one could modify its properties by altering the shape of the sheet or substrate, which means an even bigger plethora of possible uses. Moreover, being 100 times stronger than steel, graphene is the thinnest and strongest material in the world. Now, this does sound unthinkable, doesn't it? Do you need an extravagant example showing its properties? Well, here's one. A 1 square meter graphene hammock can support a large cat weighing over 4 kilograms. Yet it would weigh less than one of its whiskers. Just for the sake of comparison, a piece of paper of the same size would be 100,000 times heavier. Given such unique properties, there is no doubt that graphene would revolutionize the production of electronic and optoelectronic devices, chemical sensors, nanocomposites, and energy storage systems. This chapter is about plastics. Let's start off with a simple question. What happens if you step on a plastic cup? You've probably visualized a crushed cup, right? That would be the case unless the cup was made from or coated with Line X. Finding it hard to believe? Well then, watch how a heavyweight stands on these cups. It's not easy to crush such a cup. It can withstand even more, and the cup doesn't even need to be entirely made of Line X. A thin coating on the surface would be enough. Line X is a particularly durable spray-on protective coating made from a 2-component polyurethane. In addition to its strength, it boasts high adhesion, chemical resistance, and abrasion resistance. Line X can fully protect virtually any surface. It might sound far-fetched, but even fierce axe blows would leave almost invisible marks on a car hood coated with Line X, and the coating would still be intact. Line-X polyurethane materials are applied using specialized industrial equipment under high pressure. The sprayed material solidifies within 3 to 6 seconds. Its short curing time allows multiple layers of Line-X to be applied without drips or runs at any desired thickness. New, groundbreaking materials never fail to surprise us with what was once considered impossible. In other words, every new technology strikes us with its novelty, and nanotechnology holds a special place here. Most people believe that the prefix nano implies something ultra-modern. Many would find it hard to believe that one of the most amazing nanomaterials was created almost 100 years ago. Nevertheless, it's true, and this material is known as aerogel. In the distant 1930s, American chemist Samuel Stevens Kistler was obsessed with one unique idea: to retain only the frame of a silicate gel, replacing its liquid with air. Using a clever and rather complex method, Kistler succeeded. Consequently, in 1931, he introduced the world to aerogel, a material with some outstanding properties. Aerogel consists of a 3-dimensional nanogrid with a framework of particles sized between 3 to 5 nanometers and cells up to 100 nanometers. As you probably guessed, the cells are filled with air, which accounts for 99% of aerogel. Such a structure makes the material extremely lightweight and a solid insulator. You can easily hold 1 cubic meter of aerogel with your arm outstretched, and a millimeter-thick layer would protect you from a flamethrower. And you don't even need pure aerogel to shield yourself from a flamethrower, or any flame for that matter. It's enough to reinforce fiberglass with pieces of this material. Watch in awe as this person casually holds their palm against the wall made of this composite, even though a gas flamethrower is aimed at the other side. Aerogel's outstanding properties have earned this material 15 entries in the Guinness Book of Records. You have to admit that's quite impressive considering that the material was discovered 100 years ago. You already know graphene's capabilities and have just seen aerogel in action. Many of you are probably wondering what would you get if you tried to make aerogel out of graphene. It seems pretty tempting to combine graphene's strength and aerogel's lightness into one material. Well, Chinese experts already have a practical answer to this question. They've created the world's lightest solid material, graphene aerogel. With a density of only 0.16 milligram per cubic centimeter, its vacuum-filled variation is 7.5 times lighter than air. Without air in its pores, the material would simply hover. However, before you imagine anything crazy like a flying house, consider a few points. Although the idea of ultralight bricks sounds amazing, the vacuum-filled graphene aerogel quickly absorbs air and water vapor, making it heavier than air. Additionally, there's the challenge of enhancing the structural integrity of graphene aerogel bricks. Such research is ongoing, and some prototype samples with promising properties have already been obtained. While they are heavier than air, their weight-strength ratio surpasses every known material. One major advancement happened in this field quite recently. It turns out that a 3-dimensional graphene matrix can be printed on a special 3D printer using unique carbon inks. These 3D printed graphene aerogels have some enhanced properties that are bound to revolutionize catalysis, desalination, as well as filtration and separation technology. You would see advancements in every field that requires large surface areas, low density, high mechanical rigidity, and specific porosity. This new material is so unique that it's hard to envision a full spectrum of its possible applications right now. The unique properties aren't the only thing that can surprise us when it comes to new materials. Some of them might surprise us just with their history. For instance, the story of Starlight is so weird that it could be as well titled The 3 Mysteries of Maurice Ward. Mystery number 1. A regular hairdresser called Starlight, a polymer with an unparalleled thermal insulation properties in homemade conditions. Just watch how a raw chicken egg coated with a thin layer of Starlight remains fresh even when exposed to a blowtorch. But trust me, this goes far beyond egg preservation. One could coat a hand with a thin layer of Starlight, immerse it in molten steel, and still feel nothing. Starlight effectively protects objects against high temperatures. Moreover, unlike traditional materials like asbestos, only a thin layer is required. Another important thing is that Starlight is simply applied to the surface. There is no need to glue it or use any special fixation structures. You've got to admit that such material is indispensable for space exploration, aviation, the energy industry, etc. This leads us to Maurice Ward's second mystery. For some unclear reasons, the amateur chemist never revealed his secret. Neither agents from Boeing nor members from the UK's Ministry of Defence could strike a deal with him. Maurice Ward never sold the Starlight technology. He could have easily become wealthy and famous, but he chose to live on his own terms. The secret remained sealed and was taken to the grave. Now, you might ask, okay, that's indeed intriguing, but what about the third mystery? Well, here it goes. The public learned about Starlight in 1993. The inventor passed away in 2011. In 2013, ThermoShield bought all Starlight-related rights from Ward's family. Fast forward 2 decades, yet no one, not even ThermoShield or NASA's labs, has managed to replicate Maurice Ward's success. There's still no commercial product available, and this is the third mystery. We hope that one day science will unravel it, and we will see various Starlight applications. Despite all its amazing properties, the spotlight of our previous chapter Starlight couldn't dazzle anyone with external effects. However, Shapeshifting Nitinol is a totally different story. Just look at how it transforms. A Nitinol paperclip can be bent or crumpled, but once slightly heated, around 40 degrees Celsius, the mangled wire transforms into its original paperclip shape. This looks mesmerizing. An experiment with a Nitinol spring looks no less spectacular. Once stretched or crumpled, it becomes straight and elastic when heated. This nickel titanium alloy can remember its shape and restore itself when exposed to heat. Wondering how this happens? Let's tell you. The first thing you should know is that there are no nanoelectronics involved. Instead, the alloy has 2 structures, austenite and martensite. During deformation, austenite transforms into martensite at the bend points. When exposed to heat, the reverse transition occurs, thereby restoring the metal's original structure. Now, the true Nitinol secret is that its memory can be fully erased by heating the alloy to 500 degrees Celsius. Nitinol's thermomechanical memory has already solved problems in multiple fields, including medicine, aerospace, and aviation. In medicine, Nitinol fixators are applied to connect and straighten broken bone parts. Nitinol spirals restore the diameter of damaged vessels. In dentistry, Nitinol arches have revolutionized bite correction. In space technology, Nitinol produces self-sealing thermomechanical joints, self-straightening metal farms, as well as telescopic and parabolic antennas. In aviation, Nitinol's memory has been used for variable geometry air intake devices and serrations on the nozzle's edge. In previous chapters, what surprised us the most were the material's physical properties or mysterious shape changes. But here, the very name of the substance stops us in our tracks. 3M dry water. It sounds, at the very least, contradictory, since water can't be dry. But in reality, there's no contradiction. The dry water is actually perfluoro, 2 parts methyl, 3 parts pentanone, which looks exactly like water but has some completely different properties. Unlike regular water, nothing gets wet in dry water, not even cotton. The substance simply rolls off a paper napkin, leaving it completely dry. With such water, you can easily walk between the raindrops, pun intended. But it's also hard to dissolve anything in it. For instance, it doesn't mix with alcohol. The two liquids instantly separate, leaving a clear demarcation. We now know for a fact that dry water isn't really water. It's not drinkable, you can't clean anything with it. So how do we use it? Dry water is an excellent insulator. You can submerge a laptop in dry water aquarium and the device would still work. No issues with the keyboard. Dry water boils at around 50 degrees Celsius and evaporates rapidly without a trace. Naturally, it's perfect for extinguishing fires in server rooms, archives and museums. Electronics will remain intact, documents and paintings won't get wet. Dry water is quite fascinating, but it's not the only liquid that can surprise you. Watch closely how a ferromagnetic liquid behaves. This is arguably one of the most mesmerizing sights you can see today. It feels like its interaction with cylindrical and spherical magnets was taken straight from a world of science fiction and alien intelligence. The mathematically precise, yet unfamiliar, 3D shapes that form when the liquid contacts helical surfaces are especially mesmerizing. The dynamic visuals with surfaces appearing and disappearing all the same time are truly a joy to behold. Naturally, one starts to wonder how all of this works and why it happens. The answer might be easier than you think. In 1963, NASA employee Steve Papel was trying to solve the problem of delivering liquid fuel in zero gravity. Iron nanoparticles were added to the fuel, along with a small amount of surfactants to prevent clumping. A magnet was then used to draw the particles and consequently the fuel to the desired spot. That's it. This was the first ferromagnetic liquid. Now you know that liquids aren't just for show. Ferromagnetic fluids find applications in optics and electronics, as well as adaptive suspensions of supercars. Many beautiful experiments involve magnetic effects. Stay tuned for our next feature to see one of them. Magnet-related videos have become common these days, and they mostly involve metals. But what you're about to witness is a flat piece of graphite effortlessly levitating over a magnet. Everyone knows how challenging it is to place one magnet over another so it hovers in mid-air without sliding off. Achieving this manually is virtually impossible due to the shape of the magnetic field. However, you can easily do it with a graphite plate. What's more, the plate stays levitating even when nudged in any direction. What we witness here is stable levitation without any tricks. But how does it work? You might have guessed that the secret lies in the material of the plate. This isn't ordinary graphite, but pyrolytic graphite, an extremely strong diamagnetic substance. Its magnetic susceptibility is almost 40 times greater than that of bismuth, the best natural diamagnetic material. When exposed to an external magnetic field, the pyrolytic graphite generates its own magnetic field, oriented in the opposite direction to the former. The intensity of this inherent field depends on the external field's strength and the material's properties. Due to the pyrolytic graphite's unique qualities, the generated magnetic force can counteract the force of gravity. As a result, when repelled by an external magnetic field, a plate of this material can hover even above a regular, non-superconducting permanent magnet. You often need a strong magnet to show the extraordinary properties of materials. However, in the case of gallium, you can do without one. All you need is roughly 1 cubic centimeter of gallium, a couple of tablespoons of warm sulfuric acid, and an equal amount of potassium dichromate. Personally, using a magnet seems easier to me, but let's proceed with our experiment anyway. Introduce acid into a petri dish with gallium and see how the droplet of metal contracts. If you then add some potassium dichromate, the metal will start pulsating in a weird way. Gallium will contract and expand, pulsing at the rhythm of a heartbeat. This occurs due to the rare metal's properties. At room temperature, it remains liquid and readily wets most materials. In our experiment, the wetting properties are diminished by acid and are subsequently restored by the potassium dichromate. Consequently, the gallium droplet expands and contracts, caught in the tug-of-war between these chemicals. It's a pulsating metallic heart, a quite unusual sight. Gallium pulsation has multiple practical applications. It can be used to create chemical timers, microvalves, and mini pumps that operate without batteries. Gallium is also widely used in medicine, electronics, and electrical engineering. The average concentration of gallium in the Earth's crust doesn't exceed 0.002%, but it can still be extracted from mineral sources. Stay tuned to learn about the substance that never existed on our planet until humans invented it. Helium-2 doesn't occur in nature. It's a liquid created by humans in an attempt to reach absolute zero. While subjecting liquid helium to ultra-low temperatures, scientists noticed that it suddenly changed properties upon reaching a temperature of 2.17 Kelvin or lower. The changes were so significant that they called helium at such temperatures helium-2. This substance behaves very unusually. Let's see how. Superfluidity is the property of a liquid with zero viscosity. Being superfluid, helium-2 can permeate ceramics with pores as tiny as half a micron in diameter. No other known material can do that. There are two other experiments that vividly demonstrate this effect. If you pour helium-2 into a cup, filling it only halfway, you'll see a thin layer known as the roll-in film crawling out of the cup's sides before dripping down. Alternatively, if you dip a capillary tip tube into a container with helium-2, a fountain of this superfluid will almost instantly eject from the tip. Helium-2 is difficult to store due to its superfluidity. It constantly tries to escape from a sealed container along the walls and through the tiniest gaps in the lid. This has to be taken into account in practical applications. The behavior of helium-2 at ultra-low temperatures is quite intriguing, but let's face it, unusual properties are not that unusual when it comes to such extreme conditions. Why don't we go back to the real world and take a look at, say, europium? This costly, rare earth metal belongs to the lanthanide group. In general, it shares many characteristics with its fellow lanthanides, but has one very distinct property. Unlike its chemical relatives, europium easily forms both divalent and trivalent compounds, meaning that it can bond with 2 or 3 atoms of different substances. This unique trait opens up 2 promising application avenues for europium. Divalent europium exhibits a stable red line in its emission spectrum as part of any compound. Such property is critical for developing organic red LEDs and phosphors based on it. This paves the way for eco-friendly photonics, where atmospheric carbon dioxide is used to produce light-emitting devices. Given the rising concerns about greenhouse gases and global warming, divalent europium-based technologies may offer a timely solution. In contrast, the emission spectrum of trivalent europium varies depending on the compound that incorporates its atoms. This property gave rise to an ingenious anti-counterfeiting strategy for the European currency. EU banknotes incorporate europium elements that glow in a specific spectrum. Replicating this glow demands precise paint formula, which makes it very challenging. Thus, europium ensures a high level of anti-counterfeiting protection. What we see now clearly challenges our everyday experiences. White sneakers remain clean after being in a muddy puddle, and Pepsi Cola rolls off a white t-shirt without a trace. Meanwhile, construction materials, tools, and car parts also stay clean, even when exposed to dirt and oil. As incredible as it may seem, this isn't a Photoshop trick, but the result of applying a hydrophobic coating. Hydrophobes refer to substances with non-wettable surfaces. Liquids bead up and don't get absorbed by such surfaces. This phenomenon is scientifically known as the lotus effect, Have a look at a water droplet on a lotus leaf. It takes on a spherical shape and rolls off without leaving any trace. This effect comes down to the special surface structure of hydrophobes. They have a micro-bristle layer that traps an air pocket beneath a droplet. In the case of lotus, this function is performed by ultrafine hairs, whereas artificial materials achieve it through micron-level texturing. Research reveals that most effective hydrophobic surfaces are micron-sized bumps layered with nano-sized protrusions. These materials are categorized as superhydrophobes. This kind of material is exactly what keeps the surfaces you see right now spotless. Now that we've seen how dirt fails to stain, it's time to explore the phenomenon of hot ice. Let's keep on breaking stereotypes. We're used to the fact that ice is cold. However, you're about to see one that can warm you up. If you'd like, you can even create an ice sculpture of Santa Claus in the summer. What makes it possible is the supersaturated solution of sodium acetate used instead of water. A tiny crystal introduced into the solution at room temperature triggers the crystallization, thus forming something of an ice cube. This process produces heat, making the ice hot. This effect is utilized in the manufacture of popular hand warmers. So the next time you need a quick warm-up, just use the ice. While hot ice may warm a car driver, sadly, you can't use it to make a windshield. For that, you need robust car glass that doesn't shatter into pieces during a crash. In some cases, one needs even something more, specifically bullet-resistant glass. The bulletproof glass we see in movies is more than fiction and serves to protect people in real life. However, there's an important detail. The target remains passive and cannot retaliate with gunfire. It might seem like nothing can change this, but actually there's a solution. You will now see how one-way bulletproof glass works. Demonstrated by an employee of the Israeli firm BP Developments. A bullet from an M16 failed to breach the 2-inch thick glass from the outside, yet the inner side remained completely unscathed. Yet when fired from the inside, bullets effortlessly go through. Notably, fragments of the exterior fly towards the attacker, improving the efficacy of return fire. The outer layer of this glass consists of hard, brittle acrylic. It is followed by thin layers of bullet-resistant carbonate with an adhesive layer of transparent, thin polyurethane, which helps to absorb the bullet's energy. When the shot comes from the inside, no energy is spent on pushing hard shards inward. Instead, the bullet merely forces the hard layer outward and flies along with fragments towards the enemy. In previous chapters, you've learnt about some intriguing substances with fascinating physical properties. Now, let's delve into something different. A substance that alters not its own, but our seemingly constant physical traits specifically. The pitch of our voice. Keep watching to see how a person's voice changes. Many of us probably remember from childhood how our voice becomes squeaky when we inhale helium from a party balloon. However, what you'll see now is actually the opposite. Watch closely as a woman inhales a certain gas that immediately deepens her voice. The same happens when a man inhales the gas.
Some of that.
And my voice gets really low, although somehow I'm still funny. It's scientific!
Notably, their pitches fully return to normal upon inhaling regular air. This indicates that the vocal structures haven't changed, so why did the voice alter? The reason lies in the unique physical properties of sulfur hexafluoride. This was the gas featured in the experiment. It has a very high density and is 5 times heavier than air, causing vocal cords used to regular air to produce a deeper, lower sound. There's another impressive experiment demonstrating its high density. If you fill an empty aquarium with sulfur hexafluoride and place a lightweight ship into it, it would float on invisible waves. Such a scene would never fail to amaze anyone. You've already seen the unusual behavior of some substances with unique physical properties. However, even objects made from well-known and seemingly ordinary materials may act quite peculiarly. Now, let's take a look at a fascinating toy. The Celtic Stone. As suggested by its name, the Celtic Stone traces its origins back to an ancient artifact, first discovered in Celtic burial sites. For our demonstration, we'll use a modern replica, a commercially produced version of this item. If you spin the Celtic Stone counterclockwise, it simply rotates for a while, then gradually stops. In short, nothing out of the ordinary. The real magic unfolds when you spin it clockwise. The stone begins to wobble, then reverses its spin direction. This seems utterly counterintuitive, as nothing stops it or prompts it to spin the other way. Is this another quantum effect? Not in this case. The movement of the Celtic Stone strictly follows the laws of classical mechanics. The secret lies in its asymmetric mass distribution and instability along its longitudinal and transverse rotation axis. One can only wonder how the ancient Celts came up with such an ingenious toy. Stay tuned to discover even more mysteries. The gumbut is essentially a mathematical roly-poly or self-rightening object. It always finds equilibrium regardless of how it's tilted. The gumbut came into existence not in the lab but rather in the mind. The thing is, no such objects have been found in nature. Its shape is the result of solving a very complex topological problem. For a long time it was believed that a homogeneous convex object with one point of stable and one point of unstable equilibrium couldn't exist. In short, it was believed that a convex object that always returns to equilibrium should contain cavities or inserts made of a heavier material. A well-known example is the traditional roly-poly toy. The bottom part of this toy has a heavier insert, so whenever it's tilted, its center of gravity never crosses the support point. As a result, gravitational force always makes the toy stand upward. Here everything is clear, but the question remains. Can we make a roly-poly toy from one material without any inserts or voids? Russian mathematician Vladimir Arnold was the first to propose that such objects could exist. The solution was found by Hungarian mathematicians Gabor Domokos and Peter Várkonyi. After 10 years of research, they even proved there could be multiple solutions to this problem. They also came up with the shape that you can see on the screen. As of now, there's only one physical type of the gumbut. No other forms have been proposed. Manufacturing such a toy is very challenging, requiring processing accuracy of about 1/10 of a millimeter. Of course, everything in the real world strictly follows the laws of physics and nature. Fascinating materials challenge our stereotypes about the world around us. They teach us to embrace the parts of reality that go beyond our experience, reminding us that the universe is richer and more mysterious than we might think.